5.3 is on the IdealOpAmp. And I've left up here the answers from the last example problem we worked. If you haven't seen that video yet, take a look at it. But this was solving an op-amp problem by using the equivalent circuit. And it works, but it's a lot of steps, and it takes a long time. So we're going to look at solving the same exact circuit, but using the idea of an ideal op-amp. So an ideal op-amp, if you remember, our ideal gain is infinity. Our ideal input resistance is infinity. And our ideal output resistance is 0. So if we assume that these are true, then we can make a couple assumptions about our circuit. One is that the currents entering the inverting and non-inverting terminals, call them I1 and I2, are both equal to 0. That's because we have infinite input resistance. So remember, infinite resistance means a hole. There's nothing there. There's a break in the circuit. There's an open circuit. If we have an open circuit, we have no current. So we're making that assumption because of the Ri being equal to infinity. Our second assumption we can make is that the voltage at our two inputs is equal to each other. In other words, our VD is 0. And that would be because our gain is infinite. Excuse me. So if we make these two assumptions, it's going to make our circuit really, really easy to solve. So let's take a look at that. One thing I want to note, we're saying that the currents into the op-amp are 0. That does not mean the current coming out is 0. So do not ever assume that I.O., the output current, is 0. You cannot assume that. This is just for the inputs. So if we look at that exact same problem that we had, try to draw it quickly here for you. So again, if you haven't seen the previous video with that example problem, please take a look at it real quick. It gave us a Vs of 1 volt. We're going to label this V2 and this V1. We had an output current I.O. and a 40K, 20K, and 5K. So the book's going to show this first way to do this problem, and then I'm going to show you an even faster way. Okay, so let's look at rule number 2. V1 is equal to V2. So rule 2 tells us that V1 is equal to V2. Well, V2 is just 1 volt, so V1 must be 1 volt. There we go. We're done with that one. Where's C? I want to keep it consistent here. So we know we have 1 volt here. If I want to find this current, let's call it IA, now I can use Ohm's law. I know the voltage here is 1 volt. So I have 1 volt from this node to ground. So my IA, V over R, 1 over 5K. Gives me 0.2 milliamps. Okay, so I have that current. Excuse me. What else did I want to do here? I lost what I was doing. Oh, okay, sorry. We have 0 current from rule 1 going into our op-amp. Right, 0 current there and there. So rule 1, I have 0 current. If I have 0.2 milliamps here, that means it had to come from here. I'll just call that IB. So now I know that IB is equal to 0.2 milliamps, which is IA, because of rule 1, because there's no current here. All right, so I know that current now. So now I can find my output voltage using KVL. So we're going to use KVL, and I have VO here. VO is going to be equal to IB times 40 plus my V1, because that's across here. Or I get VO equals 9 volts. All right, so in the other way that we did the problem, we got VO is 8.9999959. That's pretty much 9 volts. If we look now at IO, IO is going to be equal to this current plus this current. So you have IB plus VO over 20K, or I get an output current of 0.65 milliamps. And so again, very, very close to what I had before. So this shows us that the ideal op-amp works. Let me show you an even easier way to do an ideal op-amp problem. So since we're assuming the zero current into our op-amp, let me get rid of all my currents here. A minute. So we're assuming zero current, right? Zero current here. That allows me to just do nodal, right? I have zero current here, so it's like that branch doesn't exist. And I can call this V1. So let's write nodal at V1. So this is an easier way. Use nodal. And you can use nodal on any op-amp problem. All right, so I have V1 minus 0 over 5K. So V1 over 5K plus V1 minus, well, this is V out, or VO. So V1 minus VO over 40K. And that's all, right? That's the only two branches coming off of V1. I'll erase my smeary marker there. Equals 0. Well, what's V1? So I did this because of rule 1. Well, because of rule 2, I know that V1 is equal to V2, which means they're both 1 volt. So now I have 1 up there for V1. So I have 1 over 5K plus 1 minus VO over 40K equals 0. And if I solve for VO, I get 9 volts. So using nodal for op-amp problems is by far the easiest way to do it. You have to pay attention to where you're doing nodal, and we'll work more examples. So you can do nodal here and here. You cannot do nodal here. Do not do nodal here. Why not? Because we don't know the current IO. We don't know what that is. We have no way to write for that branch, so we cannot do nodal there. But we can do nodal here and here, and we'll do some more example problems of that in the next video.